So as mentioned in the video, most chemical reactions actually occur in several steps. So the chemical equation that we are given is just showing the things that are present at the beginning and the things that are formed. It's not telling us about how they interacted, what intermediates they made, or anything like that. That would be the reaction mechanism. That's going to be a series of individual chemical steps that actually tell us how the chemical reaction occurs. Each of those steps is called an elementary step because it represents the exact things that have to collide and react. So the mechanism for the reaction of H2 and ICl has two steps. In the first step, the hydrogen collides with the ICl and makes Hi and HCl. Okay? These are the two actual things that are running into each other. And then the Hi that we made in the first step runs into another ICl, and that makes HCl and I2. Important thing about the mechanism is that you have to have, in order for it to be valid, if you add up those steps, it has to give you the overall equation. Otherwise, something is missing or it's just flat out wrong. So we check it just by adding these two together. And before you add equations, it's always a good idea to see if there's anything that's happening on both sides. So here we have Hi on both sides. It's getting formed in the first step, destroyed in the second step. That's why it doesn't show up in the overall reaction. It wasn't there to start with, and it's not being produced. So it gets made and destroyed. It's called an intermediate. So that doesn't appear in the overall equation. So we add those together, we get the same chemical equation. So reaction intermediates, they're formed in one elementary step and destroyed in another. Questions? Yes?
So there's ICl gas in both of the steps.
That's a good question. There's ICl gas in both of the steps. Why don't they cancel out? Because they're both on the reactant side. Yeah. And so this ICl and another ICl are required, and that's why we've got two ICLs here. It's a good question. Any other questions? Yeah.
You just figured out the coefficients without having to think about stoichiometry, right?
You mean these coefficients?
Yeah.
Yeah, we don't have to really think about stoichiometry or balancing the equation because we're adding two steps that are balanced already.
Right, so that does it for you.
It does it for you. Yep. Question?
Why did the iodine go away the second step?
Why did this go away?
Yeah.
Because when it collided with this, the hydrogen went with the chlorine to make HCl, and the two iodines stuck together to make I2. So if you can, picture atoms as being spheres, kind of like Lego bricks, but spheres, right? And they can be connected to each other, and then they can break apart and reconnect. And so when I see this, I think about a circle, a sphere that's H, and a sphere that's I. And here another sphere that's I, and a sphere that's chlorine. And most likely the iodine ends have to collide so that that bond can form, and then HCl is formed by the rest of it. Any other questions? Good questions today. So the reaction mechanism tells us exactly what's happening. It's a complete detailed description. So it shows us at the molecular level what specific collisions are going to happen. Kinetics can help us determine the mechanism. So we can measure the kinetics of the overall reaction and work backwards to write a mechanism that is consistent with the kinetics. This doesn't prove that the mechanism is correct, but you can prove mechanisms wrong this way, so you can rule a bunch out. When we talk about elementary steps, they sort of have an order as well. It involves the number of reactant particles. So a unimolecular step is just one molecule. So that molecule is actually not colliding with anything, right? Because it's just the one molecule. Something's happening. That's unimolecular. This is bimolecular. You have two reactants. Here they happen to be the same molecule or atom. You could also have a bimolecular where you have two different things colliding. So two molecules collide, bimolecular. It's possible to have termolecular, but those are really rare. So you have to get three particles colliding simultaneously with the correct orientation. Not many things work that way. Could you do four? There could be four, yeah, but that's going to be even rarer than three. Most things are going to be bimolecular, involving two things colliding. Okay, so this is dangerous. Rate laws for elementary steps can be deduced from their equations. This is only true for elementary steps. You can't do it for everything. I wish I didn't have to tell you this at all, because you're going to want to do it with everything. You can deduce the rate law from the equation for an elementary step only. So here, there's only one reactant, unimolecular. The rate law will be equal to the rate constant times the concentration of that reactant. Here we have two reactants. So this is going to be Ka squared, because it depends on the concentration of both of those. Or here's another bimolecular, A and B. Here the rate is equal to a rate constant times A times B. So both of these would be second order reactions, right? They are both bimolecular elementary steps. So if you have termolecular, these are some of the options, and you can also predict the rates for those guys. Okay? Elementary steps only. Any questions? Usually one of those elementary steps is a lot slower than the others, and that's called the rate determining step. It limits the overall rate, it determines the rate. And because of that, it determines the rate law for the overall reaction. Here's a traffic example. If you've got 3 lanes of traffic that have to merge down to 1, that's going to slow down the flow of traffic on the freeway, isn't it? You can't get from over here to over here any faster than these guys are moving in the middle. That's the rate limiting step. Beforehand, people might be speeding along. Afterwards, people speeding along, but it gets stuck in the middle. Rate limiting step. Okay? So let's look at this chemical equation. The experimentally determined rate law is this. Why is NO2 squared? Because that's what the data showed. Why is CO not in here? It's zero order. Its concentration doesn't affect the rate. Can we get that from this equation? No, we can't. So, because this does not correspond to that, we know that this cannot possibly be a single step process. So, a possible mechanism might be this. 2 NO2s reacting to form NO3 and NO, and then NO3 reacting with CO to form NO2, and CO2. This first one being slow and the second one being fast. We can write a rate law for each of the elementary steps from their equations, only for elementary steps. So for the first one, the rate will equal a rate constant times the concentration of this times the concentration of that. So NO2 squared. And CO's not in there anywhere. And then we can write a rate law for the second one, and that's going to be NO3 times CO. Does one of those match the experimentally determined rate law? Yeah, it does, that first one. This rate law matches with the experimentally determined rate law, which gives support to the idea that this is the first step in the mechanism and that it's rate limited. Any questions? Yeah.
I'm trying to connect the pieces to the last slide. So it's the first step in the mechanism. How do I know it's the slow one? Does carbon dioxide isn't doing anything in that first step?
So to know which one was slow and fast, you'd have to do an experiment. You can't just look at it and predict. Yeah. Any other questions? So in that example, the first step, being slow, must have a higher activation energy than the second step. And therefore, it's got a smaller rate constant. So the first step is going to determine the overall rate. It's like that merge down to one lane. Once you get past this, everything's going to flow fine, but you got to get through this first. So this step is going to limit the rate of the entire reaction. This first step is going to predict the rate law for the overall reaction. Any question? So, conditions for a valid mechanism. The elementary steps have to add up to the overall reaction, and the rate law predicted by the mechanism needs to be consistent with the experimentally observed rate law. If those don't agree, then your mechanism is wrong. We can't prove mechanisms. In fact, we can't prove much of anything. We can validate stuff. We can prove things false, but we can't prove things true. So you could find a mechanism that has these two conditions, but you maybe could find another mechanism that also fulfills those two conditions. And how do you know which one is correct? You'd have to do more experimentation to figure that out. So we looked at a mechanism that had a slow first step. What if we have a fast initial step? When the initial step is fast, the rate law predicted by the rate limiting step is going to have intermediates in it, and that's not going to work, because how do we know what the concentration of an intermediate is? We can't. We can know what the concentrations of the reactants are, especially at the beginning, and what he was talking about with the, you start with X amount of this and X amount of that, and then X amount at 2X, right? And you see what happens to the rate. That's called the method of initial rates, which is what we're going to do in lab today. So if you've got some intermediate in there, that's not going to work. But we can think about it this way. When the first step is fast enough, it may establish an equilibrium. So the first step is going to make its products, but then those products, that next step is so slow, it's like they're bored, so we're going to go back to here. And they're just going to go back and forth. In equilibrium, same rate, right? Forward and backwards. So here we are given a chemical equation, an observed rate law, and a mechanism, and we're asked to show that condition 1 is met, that the elementary steps add to the overall reaction. Well, how would we do that? Add them together. Again, we want to look and see if there's things that are equal on both sides. They have to be on opposite sides of the arrows. So N2O2. It gets made in the first step and consumed in the second step. N2O gets made in the second step, consumed in the third step. And that looks like it's it. So 2 hydrogens plus 2. No! I don't know why I find that so fun. Okay, so condition 1 is met. Yes?
So you can only go from 1 to 2 and 2 to 3, or can you go from 3 to 1?
The steps would happen in this order. You couldn't do this step first. Largely because this has an intermediate in it, and that wasn't present to start with. Yeah. Any other questions? And now we need to look at condition 2. Is the rate law predicted by the mechanism consistent with the observed rate law? So here we're just looking at the first 2 steps. So this is the first step, the no, and then the H plus the N2O2. We don't need to look at this last one because it's fast. That's, cars sailing off. It's not going to matter. So the first step is fast. The second step is slow. So the rate law for the second step is what's going to be important to look at. So that's going to be rate equals, well, choose a marker first. A rate constant times the reactants. H2 and N2O2. Here, the powers are equal to the coefficients. It's an elementary step. You can only do it with elementary steps. When can we do this? With elementary steps. Okay. I'm going to give you some stuff on the exam, and you're going to be tempted to just read the rate law off of the equation. And that will be wrong. Elementary steps only. Well, is this good for the rate law? No. This is the rate law that's observed. So what's predicted by the second step isn't the correct one. And one reason we know it's not correct is that N2O2 is one of the concentrations that this rate depends on. But that's not a reactant, it's an intermediate. So we can't have an intermediate concentration in the rate law. It won't work. But what we can do is from this first fast step, we can find a relationship where we can express the concentration of N2O2 in terms of the actual reactants. So fast reaction, we're going to assume it makes an equilibrium, and we even draw the equilibrium arrows there to kind of suggest, equilibrium right there. So the rate forward is going to be equal to we got 2NO, so that's no squared. K times no squared. What's the reverse reaction? Some people can see it, other people need to write it out. That's the reverse reaction. what would the rate law be for that one? It would be the concentration of N2O2. Does everybody see that? This is an elementary step, we can do it. So when we're going forwards, we've got no going to N2O2. There's two of those, so we've got no squared. The reverse reaction, this guy going back to that. This is going to depend on the concentration of N2O2. So we know that the forward rate is equal to the reverse rate. So we can take these two things and say that they're equal to each other. And I'm being a little sloppy. The K's cannot all be equal, and so let's call this K forward and K reverse, K forward and K reverse, just to point out that they're not the same number. This is the rate law we get from the slow step. The problem child here is the N2O2. We need to get rid of that. Whoops. We need this to go away. We need to express that in terms of other stuff. So we're going to take this equation that we just created and we're going to solve it for N2O2. So I can divide both sides by KR. The KRs cancel out. So the concentration of N2O2 is equal to a forward rate constant divided by a reverse rate constant times no squared. This is math. But we can substitute this in for that guy. So the rate is going to equal our rate constant times the hydrogen concentration times Kf over Kr times no squared. That's when you really mean no. Any questions about that? Well, this is starting to look like the correct rate law, but we've got too many rate constants in here. We can collect all of these guys and just call them K. So if this is, pointing at the wrong thing. So, I mean, you can think of it this way. If this is, say, 6, just nice numbers, and this was 3, and that was 1, and this is 2. Those numbers are constant. They're rate constants. And so when you multiply, divide, combine those rate constants together, they're going to give you a constant number. It's not going to change. We don't care about what the individual ones are. But if this is 3 and 2 and 1, put them together, you're going to get 6, which is what the overall one is. So we can just combine all the rate constants into 1 and say, that's K now. Any questions? Yes?
When you're substituting the number, like, ideally when you substitute the numbers in, would they add together or multiply, or just, looks like they would multiply K?
If you actually put the real numbers in there,
Yeah,
they would be, this would be multiplied by that one and divided by this one.
okay.
Yeah. Yeah, there's not any adding. Yes?
How did you determine that N2O2 was the problem?
I determined that N2O2 was the problem because this is not one of the reactants in the original equation. which, we can't see right now because it's on the previous slide. This is the reaction we're looking at. And we don't see N2O2 anywhere in there. So the rate law has to involve things that are in the actual equation, the overall equation. Any other questions? Yes?
When you set up your equation to solve for your N2O2,
Mm-hmm.
why is the N2O2, or how do you determine the exponentiation for those ones?
Good question.
KFN2.
So these are elementary steps. For elementary steps, we get the powers from the coefficients. And only for elementary steps. It's really nice and easy, and then you want to do that for everything, but it's not going to work for the overall reaction, only for an elementary step. Any other questions?
So, what technically would define an elementary step versus just looking at an equation from the
Okay, so what makes it an elementary step instead of just a chemical equation? The elementary step is actually showing which things are colliding and reacting with each other. So in the overall reaction, I'm going to get lost here. We've got 2 molecules of H2 and 2 molecules of NO. Well, are all 4 of those colliding together to have this reaction occur? No, they're not. What happens first is that 2 of the NOs will collide and make N2O2. And then one of the hydrogens is going to react with the N2O2 to make water and N2O. And this N2O is going to react with the other hydrogen and make these guys. So this is an intermediate that gets formed in the first step, consumed in the second step. This is an intermediate that's formed in the second step, consumed in the third step. We cannot see those in the overall reaction. Does that help?
Yeah, those would probably be provided.
Yeah, the mechanisms here, you'll generally be given a mechanism because, thinking them up requires a lot of knowledge. Yeah. Any other questions? Here's another mechanism problem. Ozone naturally decomposes to oxygen by this reaction. 2O3 make 3O2. And we're given the experimentally determined rate law. And we're asked to show that this proposed mechanism is consistent with that rate law. So the 2 conditions are that if you add these together, it has to add up to the overall equation. It's always going to do that in questions that we hand you. You could check it, but it's fine. And then the other thing is that the rate law predicted by the slow step, by this mechanism, has to be consistent with this. So if we look at the slow step, an elementary step, we can predict the rate law for that one. Oh, it's red now, that's fine. Rate would equal a rate constant times O3 times O, right? The reactants, and the order would be related to the coefficient. So this times this. This doesn't work, this doesn't match up with that because this has O in it and that has O2 in it. And when we look at this, O2 is a product, but O doesn't show up anywhere. And so that tells us that the problem child is the O. It's not a reactant or a product in the overall equation. Now it's going to look kind of Christmassy. So let's just embrace that. So the first step here is fast. So, as the arrows here suggest, we're going to assume that an equilibrium gets set up. So oxygen is forming, so ozone is forming into oxygen molecules and atoms, and then oxygen molecules and atoms are recombining to form O3. So the forward rate is equal to the reverse rate. So the forward reaction is O3 going to O2 plus O. And we can write a rate law for that. It's just going to be O3. The reverse reaction is O2 plus O, making O3. And we can write a rate law for that. What would it be? Yeah, O2 to the first power, and this is the forward reaction. This is the reverse reaction. You got these double arrows. Both of these are happening at the same time at equilibrium. Their rates are equal to each other. So then we can take this guy and that guy and set them equal to each other. Everybody okay with that? Let's look at our slow step rate law. What is the problem with it? The problem is it's got O in it. And O is not in the overall reaction. So we're going to take this little mess that we made and we're going to solve for O. You want to find out. O is equal to the other stuff. And then we can take that and plug it in for O and make O go away. So I'm going to divide both sides by K reverse and O2. Those guys are going to cancel out then. So O is equal to this. So I'm going to take this and put it in down here. And I'm just going to rewrite it kind of in the middle. So we had rate is equal to K times O3. And now instead of O, the concentration of O, we're going to write this guy. So that's K forward times O3 divided by K reverse times O2. Then we're just going to combine all of those guys and call that K. Okay? Rate equals K. We've got O3 times O3, that would be O3 squared. And we've got O2 in the denominator, divided by O2. So then we compare this to that. And, well, it's really similar, but it doesn't look exactly the same. What does an exponent of -1 mean? It means 1 over that. We have 1 over O2. We just need to write it differently. So the rate law that we derived from the mechanism matches with the experimentally determined rate law. So this could be a valid mechanism. Any questions? Yeah.
How does a one exponent impact another? Like, does it slow it down?
Yeah, so that's a good question. How does that -1 exponent? And the other question is, So O2 is a product, right? We haven't seen a product concentration affecting the rate before. Yeah, well, in this case it does. And that's just a whole can of worms that we're looking at the can and we're not going to open it. Yeah, so we won't see stuff like that happen. It's just going to be reactants. Any other questions? Here's another one. Predict the overall reaction and rate law that results from the following two-step mechanism. So here, they just give us the mechanism, they didn't give us the overall reaction. But all we have to do is add the steps together. So I'm making some A2, and then the A2 gets used up. That's an intermediate. It's made and consumed. It doesn't show up in the overall equation. So that must be the overall reaction. Which step is going to help us predict the rate law? The slow one. So the slow step predicts that the rate will equal a constant times a squared. Does this have a problem child? It doesn't. A is one of the reactants. Now you could ask, well, why isn't B in there? Well, apparently B is zero order. It doesn't affect the rate. When the first step is slow, everything is nice and simple. The rate law comes from the first step. Is there going to be a problem with the slow step being second or third? Yeah, probably. But there might also be an easy one, and don't do all these algebra gymnastics. It's easy. You just read it off the first step. Yes?
So, you said the rate law, the overall equation will be from the first step?
Mm-hmm. The first step involves two A's combining. That's what's really slow. After that A2 reacts with B to form the product. That's really fast. This second fast step doesn't affect the rate. The slow step is what determines the rate. Because there's no fast step before this, when we look at the rate law predicted by this slow step, we only have reactants in it. We don't get any intermediates.
So when it comes to chemical reactions, this was on that slide with the traffic jam. It's the slow rate that the slow.
Yeah, so in the traffic analogy, this slow step might be cars getting out of the parking lot. That's the first step. Once they get out of the parking lot, they just sail off. Other times, cars are moving right along, and then something causes them to slow down. And then after that, they can move. So sometimes it's the first step, and sometimes it's not the first step.
But regardless of where the step is, the slow one will determine.
Yes. Regardless of where the slow step is, you're going to predict a rate law from the slow step. And you look at that prediction, and you have to see, well, are there any intermediates in this predicted rate law? If there are intermediates, then you have to do the whole K forward and K reverse thing and solve and substitute in. Okay? Any questions?
There's no rate for the fast reaction.
Pardon me?
There's no rate for the fast reaction.
Well, you could write a rate for the fast reaction. Yeah, The rate law predicted by this would be a constant times A2 times B. But that's not going to affect the overall reaction because it's so much faster than the first one. So it's the slow one that affects the rate.